Hey there. This is kind of humorous here. Partly because Shangri is busy scaling up to where we were in 2008. He was using a deprecated version of Mahout. But let's talk about streaming instead. Now, there's only a very few minutes here for this talk. And so what I've done is do most of it in pictures. A picture's worth 1,000 words. If I can do a picture every 30 seconds, that's what, 2,000 words per minute. So the key thing about these streaming algorithms is they have to be approximate algorithms. There's a few things that you can compute exactly in a streaming fashion, but there's lots of important things that you can't compute that way. So we have to approximate. Many of these approximate aggregates can be computed online, and that gives us all of the algorithms here are that way. So there's two tricks that I'm going to highlight here. One is hashing. Hashing turns a beautiful identity function into hash, okay? Second trick is sketching. Very, very often, you can take a very large amount of data and make a very small representation, which is just as good for some purpose. Not for all purposes, but for some purpose. The trick is to find a good sketch, and all of the algorithms here use sketching of some kind, and most use hashing. So let's talk very quickly about HyperLog. It's a pretty well-known algorithm, so I'm going to go very quickly. The basic idea is if I have n samples that are hashed and inserted into a 0-1 interval, those n samples are going to make n plus 1 intervals. And therefore, the average size of the n plus 1 intervals has to be 1 over n plus 1. Woof. That means the distance to the minimum of those hashed versions is 1 over n plus 1. Also, duplicates will go exactly on top of previous things, so they won't change that. So the n that we're talking about is the number of uniques. And that means that if we have 10 samples, the minimum is going to be right around 1 over 11. I said 0.1, but that's close enough. And here it is in a much more larger aggregate style. Here we have 100 samples, and I've replicated the problem 10,000 times. And the mean value there is 0.099, 1 over 101. That tells us how many unique values there were. So what we need to do is store many, many hashed minimum values, and we can do this. And HyperLog does exactly this, and it does it by cleverly storing the minimums in very small space. Sketch to a useful aggregate. The useful aggregate is the number of distincts. Count min sketch is another way where we have popular items. We only want to know the frequency of popular items, but we don't have enough room for a full counter. So what we can do is we can hash that item, increment the count in a lot of different places, and then when we try to find out the count for this popular item, we look in all the places it might have been and take the minimum of them, hoping that no popular item would have collided with it in all of those locations. If at least one of those has only less popular items, we'll get roughly a good count. That's the count min sketch. 2 sketches so far. Like I said, lots of pictures, we got to move fast. Leaky counters are another interesting thing. This graph, which is actually very hard to see because it drops so rapidly, is a count of the word frequencies in English. This is what Zipf's law looks like if you don't do a log-log scale. But the key about this is because it drops so fast, the frequency of anything that's considerably more rare is very, very low compared to the things that are more common. And that means we can keep a table of counters for just the things that have the highest counts so far, and then periodically cull the ones that have the smallest counts. If we do that, eventually they're going to reappear into the table. And so what we can do, because we know the characteristics of this, is we can reinsert them with an average count based on how deep we're going, so that the counter table is small, things drop out of it, but when they come back, we know about how much count they should have on average, and we know how much error there is based on what the minimum count is in the table. Clever Clever trick. So the counter table is effectively a sketch. Now, here we go into algorithms that are not well known. We've had 3 so far. Streaming K-means. Now, this is really streaming K-means, not the kind that's in MLlib. MLlib has a streaming K-means assigner. It doesn't do the clustering in a single pass. It doesn't do the clustering in an online fashion. This algorithm will. It will do what is normally a multi-pass algorithm in exactly one pass. That's pretty cool. Now, the problem in K-means typically is that you wind up with clusterings like this, where because of bad initial conditions, you will split some cluster, and some other 2 clusters will be joined together as one. You can see red and yellow here are splitting that upper left cluster, and blue is sharing the 2 clusters in the middle. This is very typical. This is why you restart K-means. This is why K-means is not only multi-pass, but often you have to do restarts and run it again. But if we could come up with a sketch that would avoid this sort of problem, a small representation of the data, we could do the clustering on the sketch, not on the data. So here's a picture of data. That's the red and the green and the bluish sort of stuff. And superimposed on that is a K-means clustering of that set of data, except that I've put in way more clusters in the sketch than I would have in the final result. The result is that all of the clusters have several sketch centroids in them. And that means that I will almost always have something in every interesting feature of the data. And so I can cluster the sketch instead of the data. The other interesting thing, and there's obviously no time to prove anything in a 15-minute talk, is that you can do a very slimy job of clustering the sketch centroids. You can use an approximate distance. You can do an approximate search and just slam those babies in there. You can also adapt how many you need on the fly. And so it's really kind of a cool one-pass algorithm to get the sketch. And the sketch can represent all kinds of amazing distributions if you have enough clusters. This spiral here can be approximated with 20 clusters like that. And so any sort of clustering we'd like to do on the original data can be done on the sketch. That's the assertion. That's what's behind the proof. And that's what allows us to go one pass through the data with a very, very fast algorithm, which is only log in the number of sketch clusters I'm getting. That gives me a high-quality sketch at the end with many clusters compared to how many I want in the end. And that then I cluster in memory on one machine. Piece of cake. Sketching, again, is the key here. And very often with high-dimensional clustering, you also want to hash down to a lower dimension, especially when building the sketch. So hashing and sketching again. Final algorithm I want to talk to, and we're sitting here at 9 minutes in a 15-minute talk. It's about right. The idea here is I want to compute the quantiles of a vast number of samples. And in fact, I may want to keep millions of these quantiles for different kinds of subsets of everything I'm looking at, sort of an OLAP cube sort of arrangement, but for all the distribution. So I'm going to get an approximation of the entire one-dimensional distribution of my data. And the basic idea here is that we can do an adaptive K-means sort of algorithm in one dimension. The idea is we find the nearest cluster. If that cluster is too full, we'll define that in a moment, we start a new cluster. If it's not too full, we add the new point to the existing cluster. Now, the cool thing about that is we can choose the meaning of too full to give us very, very cool accuracy bounds on our estimate of the quantile. If we choose to have small centroids, small clusters near q equals 0 and q equals 1, what we can do is bound the accuracy So the accuracy is relative to the distance to the nearer end. If you think about it, the 50th percentile plus or minus 0.1%, it's still pretty much the median. But the 99.99th percentile plus or minus 0.1% isn't the 99.99th percentile at all. We want a much finer accuracy at the ends with lots of nines or lots of zeros. With 99.99%, we probably want 0.001 or less error. So we want relative accuracy, not absolute accuracy, and small clusters and big clusters let us trade that off and have the smallest distribution in memory. The way we do that is we then can interpolate in the quantile space versus back to the sample space. The x-axis here is the sample space, and you can see that's a piecewise linear approximation of the cumulative distribution function, and you can see how linear interpolation there follows the actual distribution quite nicely. Now, we might want to turn this a little bit. The way that these sizes are limited in the t-digest is we translate from Q, which is now on the horizontal axis, to a centroid number. And we do that by this nonlinear curve. And what that does, because it's steep near the ends, is the centroids are close together in Q space near the ends, so they have to be small. They're far apart in the middle, and so they can be large. That means our accuracy is very, very fine at the ends and coarse in the middle. What we do is, as we're clustering, as we're inserting new samples in there, we determine for every cluster whether the k value at the beginning of the cluster, before the cluster, and the k value after, that k2 and k1 here, have a difference of greater than 1 or not. If the difference is less than 1, then the cluster is small enough to have a sample added. The size bound on this data structure follows directly from the form here, the arcsine function that we use there, and the accuracy, as you can see, on real data. Now, these are two kinds of data, uniform and gamma 0.1, 0.1. The gamma function is so disturbed that the mean is 1, but the median is 10 to the minus 6th. The 0.01, or the 0.1 percentile is 10 to the minus 30th. So it's very, very skewed, but you can see the accuracy is virtually the same as in the uniform case, and near the ends at 0.001 or 99.9%, the accuracy is within a few parts per million. This is with a finite data structure and about 200 nanoseconds per sample. So what we have here, hashing and sketching are the two tricks. HyperLog log is one well-known algorithm for count distinct. Count min is a good one for doing counts. And I didn't mention, but there's also the Leaky counter for the heavy hitters. Streaming, truly streaming, online Kmeans is done with sketches. And the quantiles via the t-digest for quantiles, summaries. And we have 2 minutes for questions. I'd like to point out we have free online Hadoop ecosystem training, includes all the sorts of things. I have a series, along with my co-author, Ellen Friedman, of short books on practical techniques, kind of like this, but generally a bit more applied. The first one was on recommendations, how to go to 50 billion, not 1 billion samples on a very small cluster. Second one was anomaly detection, practical techniques for that, for probabilistic. How to go to 1 billion samples per second ingest rate on a time series database, and real-world Hadoop, which is a bunch of use cases of the Hadoop ecosystem, including Spark. The latest one is real-world Hadoop. Thank you. Are there any questions? And I hope you can talk faster than I can if you're going to ask a question, because there's only 1 minute left. Somebody up there? No, they're just headed out. Well, thank you very much.
Ted.